We'll start the quiz in about 10 minutes, but before that, let's do a review of the previous lecture and look at a little bit of the tensor playground while we have time. So if you remember, in the last lecture, we spoke about various aspects of the artificial neural network. We looked in detail at the backpropagation algorithm, which is based on gradient descent. And then we started looking at the TensorFlow Playground. And let's just directly go to that and try to understand this network. Before we actually see it live, let's take a look at the screen and try to understand what's actually depicting. So if you recall, we had looked at an example of being able to differentiate between dogs and cats, right? And here we had two parameters, two features as we've called them. We looked at weight versus friendliness, right? And we said that we could perhaps categorize the cats over here and the dogs over here if they were linearly separable, all right? So this here is an example in which they have used a bunch of data. So you can see perhaps all of these, one category of creatures, you might call them cats, and the other categories are displayed and they're linearly separable, all right? And what they've done is they've used two neurons. So this is sort of similar to our to our network where you had we had three perceptrons, but in this case, they're only using two perceptrons. And the inputs X1 and X2 are given over here. And in our previous cases, we had looked at X1 and X2 simply as individual data points. Now here, what's happening is the network is being trained through the backpropagation and gradient descent algorithm, which we've already studied. And a large number of data points have been fed in, and slowly through a certain learning rate, which is chosen to be 0.00001, they have gone through a training phase. Yes. No, there are two neurons over here. So you have a neuron over here, and notice that the X is being fed into both of these. Okay, so you have two neurons over here. And this is a simple case where you have two neurons being used, and you have an activation filter. So you're using sigmoid. Okay, you could use various different activation functions over here as well. There's something called regularization, which we haven't really talked about yet. We'll talk about this later on. And then we're looking at a classification problem. So basically, it's classifying between two types of categories. Okay, so now that we've understood this, let's also take a look at these two things over here. It says output. There are two types of output being discussed over here. One is the training loss, and the other is the test loss. Now, if you look at this curve, it's showing on the horizontal axis time, and on the vertical axis, it's showing one of those two losses. Now, these two in this case are almost superimposed. Okay, so the test loss and training loss are essentially identical, but they're both going down in time. Okay, as the network is being trained, the losses are coming down. Now, what exactly does that mean? Let's take a look at we've got too many windows opened over here. Okay, so this is a graph showing training versus test loss. Okay, and we're showing time on the horizontal axis, and we're showing vertically the loss. Now, if you think about, as I mentioned last time, training versus test loss, what's the difference? Basically, have a bunch of data, and some of it is being used for training, and some of it has been separated for testing purposes. So after you've done the training, you want to be able to test. Okay, so half of the data, if you look at the previous page over here, you can see that 50% of the data has been used for training and 50% for testing. Now you could change this ratio online on this TensorFlow Playground. So now the question is, which one is which? Do you think the red line is training or the red line is testing? Training versus testing. Which one is which? Sorry? training should be less, right? So training should be over here and testing should be up here. Why is that? Because we expect that the loss in training should be lower because this is the data that you've actually trained on. But when you're testing on new data, then you expect that it may not fit very well, okay? Now, do you think this line is going to continue going downwards? So this is clearly testing, and this is training. Now, I've shown this part of the way. Do you think this is going to continue going downwards? So you probably don't have a hunch yet, but I'm going to show you some data, and I'm going to tell you that the testing data after a while actually starts going upwards. In other words, the loss on the test data actually starts to reverse. Now, why do you think that's happening? Clearly, the training data will have a better and better fit, okay? But why should the test data start to diverge? In other words, the test data is saying, no, you haven't chosen the right parameters for the network. So think about that. We've got another minute before the quiz starts. So think about that during the quiz. Don't think too much about your quiz, all right? So we'll come back to this, and I'll let you sort of settle down to get ready for the quiz. But I think this clock is actually a couple of minutes ahead, isn't it? Okay, clock is 2 minutes ahead. So let's just continue. So the reason why the test data actually goes upwards after a while is something called overfitting. Okay, and to be able to understand what overfitting is, let's take a look at some data. So let's say you have a bunch of X and Y points, okay? And what we're doing in the first case is we're doing a linear fit. So you can see that if you have all of these data and if you do a linear fit, hopefully you've studied this in some of your courses in either calculus or some other course, you can do a straight fit, okay? This is called a linear fit. Do you think a linear fit is better for this data or a second order fit? So in a second order fit, we're trying to fit a second order polynomial, an X squared term, okay? So which looks a little better to you? The second order looks a little better, all right? What do you think will happen if we do a sixth order fit? In other words, we use a sixth order polynomial. You think the fit will become better? Yes, it will, right? So here's what the sixth order fit looks like. And you can see that in the second order, you weren't really going through all the points, right? You were going through some of the points and was doing a slightly better fit. But in the sixth order, you're actually going through each and every point, right? But do you think it's a good estimate of the predictability of the data? In other words, for example, if you wanted to predict the data, let's say that we wanted to predict the data somewhere over here, okay? Let's choose this point, somewhere between 1 and 2. Let's say at 1.5, we wanted to predict what the actual value would be, okay? You think the linear fit would be best, or the second order fit, or the sixth order fit? Sorry? Sixth order fit, you're saying would be the best at point 1.5. So when the X value is 1.5, the Y value in the sixth order is telling you what should the Y value be? Should be approximately minus, let's say 20. Just look at the data, okay? Do you think at this point, what is your guess as to what should be? Suppose these are your SAT scores, right? Horizontal axis is your SAT scores, or it could be IBA test scores. These are different students, and these are their test scores. So if you want to guess what the value would be over here, do you think it should be somewhere around minus 30, or it would be somewhere around plus 5 or so? Based on this data, which seems to be a better fit? Sorry? Linear fit seems to be better, right? Clearly, the sixth order fit has a problem. And what is the problem? It's actually going all over the place. It's going down. If you can see this clearly, it's going down and then up. It's going through each and every point. We were talking about the issue of what is referred to as overfitting. Okay. So for example, if you have this data and there is some random noise in the data, you don't want the function which is trying to estimate the data to be overly accurate. Okay, so in this case, in the sixth order, what you're seeing is that it's trying to overly predict. So in other words, it's trying to go through each and every point, and as a result of it, the curve is going all over the place. All right. In fact, if you look at this data, the actual data it may just be linear data with some kind of noise. All right. So when you're doing fitting, you don't want, and especially if you have a small amount of data, you don't want to be able to overfit. Okay. So the example over here of the sixth order is that it is overfitted. Okay, overfitted, and as a result of that, it's got a curvature which is going, it's got a function which is going all over the place. And if you try to see that, if you're trying to, let's say, estimate over here the value of y given x somewhere over here, or the value of y given x over here, it comes out to be extremely inappropriate. Okay, this is coming out to be a negative value. This is coming out to be actually lower when we know that roughly the data is going upwards. Okay, so some of them may have some randomness involved in it, in the actual data, but generally speaking, if you were trying to predict something, an x value over here, you would expect that the y value would be somewhere over here. But in this case, you can see that if you've overfitted, it's showing you a very low value of the y function. Okay, so this is called overfitting, when you have a small amount of data and you're trying to do an extremely and a very high order function. So and that is why you see over here, the problem is when you start overfitting, the test loss starts to become large. So again, why do you think the test loss is becoming large and the training loss is continuing to go down? What's the logic behind that? Let's say that at some point you're overfitting, but then how do you explain why the test loss is increasing, but the training loss is continuing to decrease? Well, you don't necessarily need less data, but the problem is that you have a certain amount of training data and you're trying to have a function which is overfitting. So it's doing a very precise fit of the training data, including all its idiosyncrasies. Okay, so if there's some error or some noise in the original data, it's actually fitting to that. Okay, and because it's fitting to the noise as well, so the function that you're getting is overly accurate only for the training data, but it is not good enough to be generalized for the test data. Okay, so if you give it some test data, then it starts to give an extremely inappropriate answer. Just like over here, when you're giving it some test data, let's say the test data is over here, it's going to give you a negative value for the y value, when we are expecting that the y value should be somewhere in the positive range if you were doing a linear fit. Okay, so that gives you some idea as to what's happening when you're overfitting. So now let's go back to our neural network, and let's take a look at what is happening over here when we're trying to use data which is linearly separable, and we're trying to use a simple two neuron network. So in this case, what you're seeing is that both of these, the test loss and the training loss, both are zero. So it's a very good, accurate fit. Okay, but what happens if you try to use something a little bit more complex? So let's try to look at data which is from here. So you can see we can choose different patterns. So we could have chosen this particular data, but now we're going to choose a different data, and you can see that this data here is sort of looking like maybe an XOR. Okay, because you can see that the orange is over here, right? So the orange is somewhere over here, and the blue dots are on the other side. Okay, sort of like an XOR. Now let's see if this will fit. So we'll use a learning rate of 0.03. So we could use different learning rates. 0.03 is the sort of the default. The activation could be ReLU, it could be sigmoid, it could be linear, it could be tan H, which we haven't talked about yet. Let's use ReLU. Okay. The rest of the parameters we're not going to worry about. and I'm going to regenerate the data. So you could regenerate the data, have a different data set. And now I'm going to start the training. Okay. So what's happening? Is it able to actually predict? So what you're seeing is that the training loss is 0.21 and the test loss is 0.16, right? So in some cases, it doesn't necessarily have to follow that particular pattern. But in either case, 21% or 16% is that a good loss function? Is that a good loss value? Let's say if it was 50%. 50% means that you're simply guessing. Okay, so you can't do any worse than 50%. If it's 25%, it means that 20%. It means that 4 out of 5 times you're actually missing it. Okay, or something like that. So, but it's pretty bad. Okay, so it's and the reason why you can see that it's trying to come up with 2 linear equations and it's trying to fit an XOR in that. If we try to redo this, it might come out to be a little better. So I'm going to redo this and run it again. So every time you run it, you may actually get different results. So you can see that this time it's actually got a completely different pattern. Okay, and if you keep on doing this, you may get completely different results. Why is that? Because if you look at the weights over here, can you see the weight over here? If you can read this, it's coming up with a weight of 1.6 over here, a weight of 2 over here, weight of 0.41, and weight of -5.2. So these are the weights that it initially randomly chose, and then it did a backpropagation algorithm, and it came up with a particular solution. G. Yeah, so we have 2 perceptrons. Okay. Yes, so we don't have the third one, but we've only got 2 in parallel. Okay. So and the width of these tells you the strength of the weight. So you can see that the weight over here is very small. It's only 0.48. So it's not really using X2 much. It's primarily using X1, and X1 is basically the horizontal axis. So you can see that it's basically both of these are sort of vertical lines, and it's differentiating based on the X1 data. It's not really differentiating between the X2 data, which is the vertical data. Okay. So now let's see, what should we do next? Shall we try to have 3 perceptrons? So let's try that. This is an example of 3 perceptrons, and this is sort of similar to what we did earlier. 2 perceptrons initially in parallel, and then a third one, which was in series. So I'm going to restart this and see how it goes. So it looks pretty bad. Both the test and the training loss is about 50%. So it's actually doing nothing. Okay. It's not doing a very good job. But what you see over here is, if you look at these shades over here, that's showing you is how are these individual neurons trying to differentiate the data. So each one of the perceptrons can only do a linear differentiation. Okay. So if you look at both of these are trying to do they have vertical lines over here, and they're trying to differentiate between only based on X1. Okay, they're not really using X2. Let's try to redo it and see if they do it any better. Again, now they've got a horizontal line that's just coming up. So as you can see that, you're initializing based on random numbers, and it's doing back propagation. It doesn't necessarily always work. Okay. So in this case, you can see that somehow these 2 neurons are selecting data based on sort of a leaning line over here, a slanting line over here. And this neuron is combining these 2, and now it's differentiating between 3 areas. Okay, so it's using this neuron to differentiate between these 2 regions, and this neuron to differentiate between these 2 regions. And when it combines these 2, it can now differentiate between 3 regions. Okay, but still it's not able to do a very good job. The loss is still about 12–16%. Okay, yeah. Okay, over here, basically, you've got 2 data. So remember that we had the horizontal and vertical axis when we were using weight and friendliness data. So weight was on the horizontal axis and friendliness was on the vertical axis. So this is how it's showing it. X1 is sort of the weight, which is the horizontal axis, and x2 is the vertical axis. So you can think of x2 as being the friendliness feature and x1 being the weight feature. Okay. Yeah. Why are we sorry? Why are we not adding it? Because I want to show you what are the problems with the basic 3 neurons. And slowly I'm going to keep on adding and see if we can actually solve it with a larger number of neurons. Okay. So you've guessed what I'm going to do next. I'm going to add more neurons. Well, in this case, I haven't added more neurons. I've simply rearranged them. Okay. So I'm going to restart this just to show you how it happens. So in this case, as a little while ago, you saw that it did a pretty good job, but it's taking time. So I'm going to speed up the learning process. So I'm going to go at 0.1. Okay, so you can see that if I increase the learning process, the learning rate, it is able to find a solution pretty fast. In fact, the training loss is now exactly 0, and the test loss is also exactly 0. So it's been able to differentiate between all the 4 quadrants exactly, okay, using these 3 neurons. And you can see all 3 of them are being used. This one is being used to differentiate horizontally. This one is being used to differentiate vertically. And this one is being used to differentiate on the diagonal axis. Okay. So based on that, it's been able to differentiate between all 4 quadrants. Okay. It's interesting how it's doing, and it's done it completely randomly, just through backpropagation algorithm. And if you look at the weights it's chosen, the weight over here is negative 0.25. This is also negative 2.2. This weight is not being used at all. It's negative 0.26. Okay. So you can see that these 2 guys, these 2 neurons are using basically x1. And this one is not using x1 at all, right? It's simply using x2 primarily, but it's also using, and this one is using both x1 and x2, right? So this one is differentiating based on x2 values. This one is differentiating based on x1 values, and this one is using a combination of x1 and x2. And that's why it's got the horizontal line. Yeah. Yes, and we'll see that. X1 is not being used in the third one at all. You can see that this line is almost 0. The weight is 0.27. It's very small. So this is also back. The magic is in the back propagation. All right. No. So this is what machine learning is all about. Nobody is actually going around and deciding what the weights are, how to actually decide. This was the old technique. Okay. Before machine learning, if you don't have the learning part, people would actually physically try to figure out what's the best way to train this, or the best way to find a function which would fit it. Okay. And people spend the entire lifetimes trying to figure out the best function that would be able to predict the result. Okay. But ever since machine learning came in, the concept was that the system would learn based on the data. Okay. So this is where and this is good and bad. All right. Why is it good and why is it bad? Exactly. It's good because we computer scientists lose a job, right? Because we don't have to do any programming. The data is actually doing the program. So you can think of it as good and bad, right? It's good because it actually does a good job. All right. And you don't have to physically spend hours and hours trying to figure out what the ideal weight should be. But why is it bad? And yeah. And you're saying that's why it's bad. Okay. So what you're saying is that the bias can creep in and can actually give you an inappropriate, prediction. Yes, if you have a small amount of data, you can have very poor prediction. Okay. But there's another reason why it's bad. The other reason why it's bad is because we don't really know why it actually picked those weights. Okay, it just got those results using backpropagation, and somehow it got the answer. But if you want to ask the question why, it will not. Neural networks will not be able to answer you the question. give you the answer to the question why. Okay, why is this working? We don't know. It just works. Okay, it's got a function. It's what is called a universal function approximator. This is basically what it's doing is it's trying to figure out a function which can map the input to the output in the best possible way. And it's somehow using a neural network with the appropriate weights and biases, it's able to approximate the input. It's able to find a very good fit between the input and the output. Okay, but why does it come up with that particular function? We don't really know. It's a black box. Okay, but lately a lot of people have been starting to work on the research, in the area of research, where you try to figure out what is the answer to why in neural networks. Okay, so that's called explainable machine learning, and that's a very interesting research because people want to know why. So, for example, if you're doing a medical diagnosis and you know that giving this medicine solves the problem, or getting this vaccine gives you delivery from COVID, but you don't know why it's actually working, that's not very good. Okay, so you always need to have an answer to why. So let's keep going. Let's look at a few more examples. So this was a quadrant. So this was an XOR example. Let's take a look at this example, which is more complex. It's sort of concentric data. Okay, so you can see that all the blues are in the middle. Let me just regenerate the data for you. Regenerate the data and stop over here. So you can see that all the orange is outside in the circle and the blues are inside the circle. Okay. Now, if I try to use a 2-neuron network, will it work? Not really. It's simply trying to come up with 2 linear equations, right? And this is clearly not the solution. Now, interestingly, what you can see over here is that you can also give it x1 squared data and x2 squared data. So what I'm going to do is give x1 squared and x2 squared. And now let's try to see if it works. Okay, so let's start it. And you can see immediately it found almost a 0% loss case. Now, what's changed over here? Instead of giving just x1 and x2, I gave it a function of x1 and x2. Okay, so you can think that I've actually changed the feature. I mean, I'm looking at a slightly modified feature. So instead of the weight, for example, or the friendliness, I'm actually using weight squared or friendliness cube or something like that. Okay, so if you use the appropriate feature, you can see that you can get very good results. Okay, so it's very important to pick the right features if you want to get a good result. All right, let's take a look at another example, and you can play with this on your own as well. So this is now a more complex case. Okay, so here the data is, as you can see, it's sort of a spiral. It's 2 spirals which are nested inside each other. Okay, the orange spiral is going like this, and then the blue spiral is also going inside, and it's a very complex. So the question is, what will work? So let's regenerate the data, which means it gives a bunch of new random data. And now I'm going to try to use just 2 neurons. Clearly, 2 neurons is not going to work. Okay. Now I'm going to try to use 4 neurons. Okay. And as you can see, this has been going on for a while. Now, somebody had asked me what happens when is it possible for the test and training loss to go all over the place? You can see that that's happening. Okay. So initially it started off, and now the test loss is actually worse than when it started off. So even 4 neurons is not working out. Now I'm going to really hit it hard. Okay, try to give maximum number of neurons that I can think of. This thing can go up to like 8 layers deep, and I think 8 horizontally as well. So here's another example which I had let go a little while ago. You can see this case where somebody had asked, can the losses go up and down? Okay, so you can see that the losses can go up and down, and here it's found it's not done a good job. It's got 32% losses. Let's look at another case. This is a case which I stopped earlier, and you can see that the loss has incredibly gone down to 0.001 for training, and for test it's 0.008. Okay, so this is probably as good as you can get. Now, what's interesting about this? We've been able to solve this problem using sort of a deep neural network. Why is it deep? Because now there are 1, 2, 3 layers in depth. Horizontally, we've got 4 layers. Okay. So you can consider this as a somewhat of a deep neural network. What's also interesting is if you look at these patterns, if you look at these, now what you can see is that each one of these neurons is actually focusing on some portion, some feature of the actual data. Okay, so let's take a look at this. This is focusing on some features in the center. Okay, this is focusing on some data over here, and so on. Okay, you can see that each one of them combined together have now been able to do a good job. Okay, let me show you another example which is a little bit better to understand. Yeah, this is the one. So if you look at this, you can see that this particular neuron over here, and take a look at some of these neurons. So they're actually fitting into part of the spiral. Okay, this portion is focusing on a part of the spiral. This is focusing on a different part of the spiral, and so on. And so as we go forward in the next lecture, we'll talk about how different neurons actually focus in on different portions of the network and try to get certain features out of the network. Okay, and this will become very important in the next part of ANN, which is going to be focusing on what is referred to as convolutional neural networks, CNN.